The deformation operators are powerful high-level tools for manipulating the geometry of objects. However, users struggle to control as many as 14 different parameters in this 2D array of sliders. These one-dimensional sliders have a number of disadvantages. First, they consume a great deal of screen real estate. Second, they artificially separate related parameters from each other, such as the three components of a vector or point. Lastly, they remove all controls for parameters from the 3D view of the object, increasing the distance between user intention and their actual effects. We can see how difficult it is here to relate the positions of the sliders to the actual deformations performed on the object. A 3D direct manipulation interface can be developed for deformations. However, this kind of interface must fix most of the parameters of the deformation and map mouse gestures to the one or two remaining values. Here, the mouse gesture controls the twist angle of a deformed cube. Unfortunately, like the gestural techniques for transforming objects described earlier, this interface does not display its affordances, and there is no feedback beyond the visible twisting of the object. Since 2D widgets and 3D direct manipulation are inadequate controls for such an inherently complex three-dimensional operation, we introduce a rack into the 3D environment which directly modifies parameters of the twist deformation. The upright bars of the rack control the amount that each end of the object is twisted, as well as the range of the operation. Our original rack combines the twist, taper, and bend operations in a single widget. With 3 handles, we control 10 degrees of freedom with 1- and 2-way constraints. The angles and positions of the bars control and indicate the parameter values of the deformations. The handles are modeled to look like actual handles so that they invite twisting or moving, but they do not indicate what their functions are until one actually pulls on them. By introducing a suggestive visual representation for each of the handles, the rack widget becomes more self-disclosing. For instance, the twisted shape of the twist handle indicates its function. By pulling on the twisted handle, the object twists in direct proportion to the angle through which the handle was rotated. When we push down on the taper handle, the object is made to taper down to the height of the bar. When we pull on the bend handle, the object bends in the same direction. All of the operations occur in the range between the 2 twist and taper handles. The rack itself can be manipulated to change the axis along which the deformation is applied. In the following sequence, we can see how a rack that combines several operations can prove to be overwhelmingly complicated. This particular rack incorporates elements of many of the racks already shown in this presentation. There are 2 handles for the twist deformation, 2 for taper, and 3 for bend. 3D ring sliders have been added to control the magnitude of the deformation operations. This rack may be too cluttered to be useful. From our experience, it can be easier to sequentially apply simpler racks, like some of the examples shown earlier, just as a woodworker would sequentially use a number of different specialized tools to create a complicated shape.